Hi, welcome to Applied Math. In this section 8.3, we're going to discuss triangles, regular hexagons, and various other objects. These can be grouped together as called polygons. Polygons, many-sided figures. So even rectangles fall into that category. Triangles, any three-sided, four-sided, five-sided, six-sided figure, and etc. So let's look at triangles first. We discussed some of this in a previous video, but just to go over it again. Triangles. We have a right triangle, and this is going to have a 90-degree right there. That's a common triangle we use. We also have an equilateral triangle. All the angles will be the same, and all the sides will be equal. Equilateral. We also have a isosceles, where two of the sides are equal. And these two angles here, the base angles, will be equal also. Call this angle A and B, C. A will equal B. And that's isosceles. 1L. I think I go twice then. Okay, and then we also have another triangle. And it could look a little bit like a right triangle sometimes. But as long as it doesn't have the box, it means all the sides are different. Maybe this one is 3 and 5 and 6. This is called a scalene. Scalene, all sides different. Different. So all the sides are a little bit different on a scalene. So we're going to discuss these a little bit right here. So let's look at a right triangle just a little bit more. These two sides right here are called the legs. And this distance right here from one end is the longest side. The longest side is called the hypotenuse. Usually the 90-degree right there. This only works for a 90-degree triangle. It's a right triangle. 90 degrees. And this side we usually call C. And the distance opposite that is called the hypotenuse. So this would be angles we usually use capital letters. This could be A and this could be B. A, B, C, like that. Or it could be BCA. Okay, but the small sides, the sides opposite these, we use lowercase. So this is angle B, this would be side B. If this is angle C, this is side C, the hypotenuse. Hypotenuse is always opposite the right angle. And then this would be side A, opposite A. You kind of look like you're going down, that's the opposite. So that's usually how we designate them. Makes it a little bit easier. So in the book, they have some problems here. Take a look. Let me put this down a little bit so you can see it a little bit better. Twist it around. Okay, there we go. This is a right triangle because you see the little box. This is an equilateral because all the sides are the same. All the sides are different. Well, two of the sides are equal. So that would mean that this is probably an isosceles. Doesn't look like it the way it is, but because two of the sides are equal, this is isosceles. This one right here, let's see, 12, 12, and 17. D would also be isosceles. Two of the sides are equal. Here we can tell this is 60, 60, and this would be 60 equilateral. This looks a lot like a right triangle, but it doesn't have the little box, so it's scalene. It's a scalene triangle, and you notice that all the sides are different. They can be different on a right triangle too. So let's suppose we had a right triangle. And let's draw one right here. We have a right triangle. And let's call this side A. And this side B, B for the base. And the longest side C is, what is it called? The hypotenuse. Right here. And let's suppose we knew a couple of these sides. Let's suppose we knew that this side was 3 and this side was 4. But we wanted to find a hypotenuse. We want to find that longest side. Well, a guy named Pythagoras, hundreds of years ago, might be the oldest formula that we have, came up with this formula right here for finding the hypotenuse. He said that A squared, side A squared, plus B, side B squared, equals side C squared. It's one of the oldest formulas there is. It's called the Pythagorean formula. And it was developed by a guy named Pythagoras. And he had kind of formed a religion where mathematics was the most important thing. Smart man. And it was probably 1,000, 2,000 years ago. I don't know, a long time ago. Anyhow, let's say we want to find side C here. We got 3, 4. C is always the longest side, remember, it's the hypotenuse. So we would put this into the formula, 3 squared, side B, 4 squared, equals C squared. So first we'd square these, 9 plus 16 equals C squared, and we add them together. The only problem we have is that doesn't give us C. We want side C. So we have to do something called taking the square root of both sides. The square root of C squared is C. The square root of 25, where you can, we've got the root, we've got the square, and we're looking for the root. We can look it up on a calculator. We just hit second x squared. Let's turn that on for a second. X squared, 25. Let's put it down here. Parentheses equals 5. So this is a very famous right triangle. 3, 4, 5. We use it a lot in construction. If we're going to lay out batter boards to make sure everything is square, we can lay out something 3 foot by 4 foot and then measure across to make sure it's 5 foot. So we do use this a lot in construction. We can also use, so C was equal to, if we took the square root of both sides, it's equal to the square root of A squared plus B squared. But you would want to square these first, then add them together, then take the square root in that order. Square, add, square root. Just to make it easier, sometimes we know the longest side, we're trying to find a different side. If we were trying to find A, that would be the square root of C squared minus B squared. Here we have a minus because this is a big number, smaller number. Again, square, subtract, then square root. And B would be C squared minus A squared. So these are what we call variations of the main formula. Okay, so you get an idea. So let's try a couple examples here, okay? Let's say we had this drawing right here. And this distance here is 22.3. And this distance here is 13.8. And let's say these are feet. What would this measurement be? Well, first of all, let's figure out what side it is. This is your right triangle. So this would have to be side C. This is the bottom, so we would probably call it B. So it looks like we're trying to find A. A is equal to the square root of C squared minus B squared. A is equal to the square root of C, which is 22.3 squared, minus B, which is 13.8 squared. A is what? Well, let's square 22.3. Turn on a calculator. 22.3 times 22.3. This is the square root of 497.29. Let's make that 2 a little bit better. And we could also do 13.8, 13.8. But this time I'm just going to hit my square key down here. See if I can scoot this up a little bit. Square key. And that'd give me my answer too, 190.44. So the next thing I want to do is subtract those two numbers. 497.29 take away 190.44. That gives me A equals 306.8485. The problem with this calculator is that to take a square root, we have to kind of get out of that. So we're going to hit second x squared. We have to put that number in. That's why it's good to write it down. And finally, we can take the square root of that and get to our answer. A is just 17.5. We're round off to just one decimal point. And we've got our answer. Let me double check it. And that is correct. Now, there might be other ways you could do this a little faster, but I just wanted to kind of show you what we're doing here. We squared this, we squared this. Sometimes you can enter it all in like this into your formula, but you have to be kind of a little careful about that. So we don't want to get into it. So that's how we find the missing side. If we're finding side C, it's usually a little bit easier. But if we're trying to find one of the other sides, a little bit more difficult, but we've got a formula. So we can put it in. And you might want to practice some of those. Okay, let's try to find something else. What if we wanted to find the area of a triangle? How do we find the area of a triangle? The area of a triangle is equal to base times height divided by 2. Some people also write it as 1/2 times the base times the height. I personally prefer this one because it doesn't seem as intimidating as having a fraction in it. So let's try this on a triangle. We have a triangle. We know the distance, the height has to be perpendicular to the base. So this would be our base, and this would be our height. And we're trying to find the area inside this triangle. Okay, so we'd have to have some measurements. Let's see if we can get some measurements in here. Let's say they gave us this problem right here. You got 10, 10.6, you've got 8, and you got 13. And these are all in inches. Okay, again, they gave us more formula, more stuff than we need. We don't need these. All we need to know is the base and the height. area is the base, 13, times the height, 8, divided by 2. You could divide first and then multiply, or you can multiply and then divide. I'm going to multiply and divide. 13 times 8 divided by 2. 52. And we're going to measure that in, even though this is a triangle, inches square inches. See, just that easy. Okay. Let's suppose they gave us this problem. And we know this distance, and we know this distance, but we don't know this distance. We know this is a right triangle, but we need to find this distance, and we want to find the area. How are we going to do it? Well, first we got to find this distance. We call this B, call this C, because it's opposite, right? Hypotenuse. So we're looking for side A. A equals the square root of C squared minus B squared. A equals the square root of 10.3 squared minus 6.5 squared, and then the square root of that. So I'm going to enter this into my calculator this way. I'm going to hit the second x squared to get the square root. I'm going to put it in just the way it's written with the parentheses. Well, I think I can do it without the, well, it already shows the parentheses, but I really don't need to do that. So let's just go 10.3, and then I'm going to hit my x squared key, squared, minus 6.5 squared. And then I'm going to put my parentheses to kind of end it. 7.99. 7.98. Well, if we round that off, that would be approximately 8. So let's call A 8, just to make it easier. Now let's try to find the area of the triangle. So we're going to use a capital A. The area is the base times the height divided by 2. That's going to give us the base, 6.5. And now we know the height, 8, and we divide by 2. And we can find that out real fast. Yeah. Clear that out. 6.5 times 8, divide by 2, 26. So we would call this 26 feet squared, approximately. Okay, so we first had to find side A because it was a right triangle. Now, if it wasn't a right triangle, then we'd have much difficulty trying to find that side. Okay, now on the next page, they give some formulas here. And I don't have this exact formula. They give a formula for the isosceles triangle. I thought there was a shortcut to this one. Kind of a complicated formula. We're not going to worry about it. But let's see about an equilateral triangle. The area of an equilateral triangle and I'm going to abbreviate triangle that way, is they give a fancy formula, but the formula you really want to know is A equals 0.433, kind of a constant times A squared. And that'll give you the area of an equilateral triangle. In this book, when you have a missing side, they call that A. So an equilateral triangle, all the sides are equal. So let's say this side right here was 18. We know all the sides are going to be 18. And area is just simply 0.433 times 18 squared. We have to square the 18 first and then multiply by that constant. So you always power first, 18 squared, then times 0.433. 140.292, we just rounded out to 140 roughly. 140 centimeters, square centimeters, or 140 centimeters squared. There we go. Okay. So pretty easy to do. If we know the side, we can just calculate it. Okay. You can get into a whole thing. Another one that we can do sometimes. Let's say we don't know the height of an object and we want to find the area. This is known as Hero's formula. It was developed, or Heron's formula. The book calls it Heroes, and sometimes they do call it that. It was developed by a king, an ancient king came up with this idea. Suppose we had this triangle here. It's not a right triangle, and the sides are 5, 6, 7. And to figure out the height is really difficult to do. We don't know how. So Heron came up with an idea. First thing he did was figure out this, they call it S. It's just something we need for the formula, okay? And S is equal to the sum of the sides. Maybe that's why they called it S. You're going to add these together, and then you're going to divide that by 2. It's the sum of the sides divided by 2. But that's not the area, okay? But we want to add those up. Maybe I can just do it in head. 5 and 2 is 11, plus 7 is 18, divided by 2 is 9, okay? So I calculate that out. I got 9 for this. And the actual formula that he came up with is the area is equal to the square root of S times S minus A, side A, S minus side B, S minus side C. Weird little formula. So it's a 2-part formula. Part 1, you find S. You add up the sides. Part 2, you use this formula, S minus A. So let's call this side A. Let's call this side B. We'll call this side C because it's the biggest number, but it's not really the hypotenuse because this is not a right triangle. So area equals the square root of 9 times 9 minus A, 9 minus B, 9 minus C. So that would be the area is 9 times 4 times 3 times 2 on this particular formula. So let's multiply, and then you're timesing these all. So the area is 9 times 4 times, oops, how did I plus get in there? Times, just want to put that plus sign in, times 3 times 2, 9432, okay, 216. Now I got to take the square root of that. Second, x squared 216 equals. So the area is about, I'm going to round it off to 1 decimal point. See, the 9 is pretty big, so I'm going to round it up 14.7. And again, these would be in inches. This would be inches squared. So that's how we kind of do it. So pretty easy to do, huh? So first you find the area, find S, and then you do this. Kind of weird little formula, huh? Well, here's another little formula. We're going to work with something called hexagon, this little goodie. Okay, a hexagon, all these angles are 60 degrees going around this thing. And this isn't really drawn too well. So there's a formula for the area of a hexagon. Let me put it up here a little bit. The area of a hexagon is equal to, and they have a little formula here, 2.598, almost 6, huh? 2.6, you could almost round it off to, times a squared. So what is A? A is the side. The distance from here to here is called A. A is the side. So let's say this side was 6 inches long. A equals 2.598 times 6 squared, or 36. So I'm going to take 2.598 times 36, 6 squared, 93.528 inches squared. If they wanted to round it off, then remember the number behind the 2 is small, so we could round this to 93.5 if we wanted to. What if we took 2.6? What if we change this to 2.6? If we took 2.6 times 36, you see, 93.6. You wouldn't be off too much. You'd be off a little bit, but not great. Okay, another thing, the reason they're showing you hexagons is because we use hex bolts in, mechanics and stuff like that. The distance between this flat side and this flat side, these are called flats. We call that F. Okay? Flats are equal to 1.732 times side A. I know, weird. Or if you have the flat and you're trying to find side A would be equal to 0.57. This is in your book on page 545. But in case you don't have it, write this down. Pause the tape, write this down. 0.577 F. Write that a little bit better. Sorry about that. So if you know the flat, you can figure out the side. If you know the side, you can figure out the flat. Okay, flats. But also, let's turn this over. Sometimes we have the diameter. The diameter goes from a point to a point. It's a little harder to see this. Let me just trace it around. Blends in with the paper, kind of. There we go. So the diameter is from this point to this point. That's what we call the diameter. It goes from point to point. Flats went from flat to flat. Diameter goes from point to point. Okay, and the diameter, let's see, there's a little formula. Remember this distance right here, it's A. So the diameter is equal to twice A, kind of like the diameter of a circle, huh? Or A is equal to half the diameter, or 0.5 D. So it's kind of like a circle with the diameter and the radius. That's probably why they call it a diameter. but flats are a little bit different. Okay, so that's kind of an interesting little goodie. So let's try a problem here. Let's suppose we have a drawing here. And we happen to know that this distance right here is a 1/4 inch. Well, we'll call it 1/4, but we could also call that 0.25. And we want to know what are the flats? What is F? What are the flats? So you can use a capital F if you want. The flats are, what was our formula? Bingo, let's bring it back. It's 1.732 times A, which is 0.25. I would just use them both as decimals, not get involved with fractions. So 1.732 times 0.25 is 0.433. And maybe these were in inches. What's the area? The area is, let's go up here, 2.598 times the side, 0.25 squared. Put in our calculator, 2.598 times 0.25 squared. I'm going to hit my square key, my x squared key, equals. The area is 0.162375. So maybe carry this out 2 places, 0.16. And this would be inches squared. Okay, so you kind of have an idea what to do. Some of these are going to be a little tricky. You want to give them a shot. On page 563, they have a whole bunch of drawings. See if you can figure out those areas and things of those. Find the missing dimensions. And on the next page, they want you to find the areas. We didn't worry about some of these things, but 1 through 10 on both of these would probably give you a pretty good idea how to do these problems. So give it a shot, see what you can do.